Hey guys, today we are going to be calculating the amount of ATP, NADH, and FADH2 from a single glucose molecule, basically by doing a brief overview of like a cycle of cellular respiration. And that cycle is going to consist of a couple different cycles, which I kind of broke down into four main steps. I'm going to run through the most straightforward pathway and assuming that oxygen is present because that'll take you on a different, less energy yielding, less ATP yielding pathway. So assuming oxygen is present, we're going to start with glycolysis, which is going to yield 2 ATP, and we'll come back to this chart once we've kind of gone through all the different pathways. So yeah, glucose is going to enter the molecule, and through substrate level phosphorylation is going to give us a net of 2 ATPs. And like I said, we'll go over this a little bit more, but most importantly, it's going to give us this vital pyruvate, 2 pyruvate molecules, which will eventually be turned into the acetyl coenzyme A through pyruvate dehydrogenase, and the acetyl group is going to act as a carrier into the citric acid cycle. So glycolysis is going to occur in the cytosol of the cell. I kind of zoomed in, so here's the general reaction. Kind of shows you the stoichiometry of glycolysis, and then here's kind of the steps and enzymes that catalyze glycolysis. So we're going to start with this glucose up here. It's going to be catalyzed by hexokinase by using 1 ATP here into ADP. And then down here that we get this fructose 6-phosphate, that's also going to use 1 ATP to turn that into fructose 1,6 bisphosphate. Basically just kind of going over like where we're using ATPs and then where we're going to be using NAD plus to get NADH. So here we can see an NADH being NAD plus turning into NADH by glyceraldehyde 3-phosphate dehydrogenase, and then here's where we're going to start to actually see some ATP returning. The first step of glycolysis here is actually not going to give us, it's not going to produce any ATP, it's actually going to net us -2 ATP, but that is useful in catalyzing the fructose 1,6 bisphosphate and the glyceraldehyde 3-phosphate because the 2 molecules of ATP used in forming fructose 1,6 bisphosphate, they're regenerated in the creation of the two molecules of the 3 phosphoglycerate here, and from there we're actually going to start netting some ATP. But like I said, this is not the most important. The 2 ATP that we get from this right here, and the 2 NADH we get are not going to be super helpful in creating the amount of ATP we need for our body. It's basically going to be most helpful giving us these 2 pyruvate molecules here. So in that, ADP is turned into ATP, and then pyruvate kinase is turning this phospho-phenylpyruvate into pyruvate, which we are going to be using in the pyruvate reaction into acetyl coenzyme A, which is going to basically act as a carrier into the Krebs cycle. So like I said, we've kind of already gone over the mechanisms by which this 1,2,3 carbon molecule is turned into this 1,2 carbon acetyl coenzyme through pyruvate dehydrogenase and TTP. So I think the most important thing to get from this is that we're getting 1 NADH for each pyruvate molecule that is entering the mitochondria from the cytosol. And yeah, so CO2 is going to be one of the byproduct or one of the waste products, but most importantly, we're getting a net of 2 NADHs and this acetyl coenzyme, which is going to be able to coenzyme A, which is going to be able to carry the acetyl group into the probably the most important in energy production, ATP production, the Krebs cycle. So the citric acid cycle or the Krebs cycle, it looks and is incredibly complex. So basically, we're just going to kind of go over each step of when NAD is being reduced to NADH. So you can see 3 times here, and then we'll just kind of do like a very quick overview of how the citric acid cycle takes the 4-carbon molecule, oxalates, and condenses it to the 2-carbon acetyl unit to yield citrate, the 6-carbon tricarboxylic acid. And the 6-carbon citric acid molecule gets broken down to oxalic acid again. So it can accept the 2 carbons, and then coenzyme A is used to decarboxylate pyruvate again. So it's just a big cycle. It just is able to keep going because of those steps. And then as we continue down the cycle, we can see each time the NAD plus is reduced to NADH 3 times, and then so that happens per pyruvate molecule. So 2 pyruvate molecules go through, and for each time, so that's going to net us 6 NADHs, as well as an ATP molecule being generated here, or GTP. So those are going to be used, basically all these NADHs and ATP or FADH2s are going to be used in the most important step of the process, the electron transport chain. The electron transport chain is a series of electron transporters embedded in the inner mitochondrial membrane, and they shuttle electrons from NADH and FADH2 to molecular oxygen. In the process, protons are pumped from the mitochondrial matrix to the intermembrane space, and oxygen is reduced to form water. And then we'll just kind of go over how that is able to generate the, comparatively, compared to the other steps, the massive amount of ATP that our body is going to require for just general function and cellular respiration. So during the electron transport chain, we're basically going to, through oxidative phosphorylation, it's going to cause NADH to give up its electron in the first complex here, as well as FADH to give up its electron in the second complex. And because of that, we're really going to see these reactions start to produce a lot more ATP. So for every NADH that enters the electron transport chain, we get 2.5 ATP. And similarly, with for every FADH2 that enters the electron transport chain, we're going to get 1.5 ATP produced. So if we take the 10 NADH here times 2.5, we're going to get 25 ATP produced. And then for every FADH2 molecule that enters, we're going to get 1.5, so that's going to be 2 ATP molecules produced. And then if we take the net ATP molecules here, 2 from glycolysis, and then the 2 that were produced during the citric acid cycle, we are basically going to add up to the net average of 30 ATP produced throughout these various reactions.